the School of Engineering, University of Tokyo. And I will talk about metal oxide nanowires and how do you integrate them into devices that we're talking about. So I showed two examples of integration of nanowires. The first example is a photoresistor, very simple device made of two thick layers between which you bridge nanowires. So for detection of light, you need a plus and minus, and you need a sensing nanowire that bridge the two layers. So it's a very simple design. The point of this is that it's bottom-up technique. So it's just one single step course. And the second example, I call that horizontal integration. So we get the nanowire in the same plane as the quartz substrate. And the second example is the vertical integration devices. So where you have the vertically aligned nanowires like that. And for that, in that case, the plus and minus that you need are up there because you have nanowires that are connected at the bottom. And the connection to the nanowires are made with an electrolyte. Okay? So this is basically a sensor that can work in air, and that needs an electrolyte. And I use that to split water. It means to provide hydrogen, to generate hydrogen from water. Good. So we go to the content of the slide. So UV sensing. First, I briefly explain what I do with UV sensor. And UVA is very well known. I explain briefly what is deep UV and why this is important and how do we detect that. The second part is water splitting with core shell nanowires. So in that part, I use nanowires on film structures as a template to do water splitting. So these are two parts. So I come to the UV sensor with the bridge technique. Okay, so you all know very well about UVA. So UVA is between 400 and 320 nanometers. And to detect the light selectively, you need a band gap of 3.3 electron volt, which is for zinc oxide is exactly that band gap. So zinc oxide is a good material to detect UVA. And for UVC or UVC, deep UV, this is harmful, so very strong radiation that can damage DNA. It's below 280 nanometers. So this is a very interesting part of the radiation because it's absorbed by the atmosphere, and therefore on Earth's surface you don't have UVC radiation here. So this is the solar radiation on Earth, and below 280 nanometers you do not have radiation here. So that provides you with a clean background for detection of light cells that emit the UV, like a flame. A flame can be a fire, it can be a missile, etc. So one famous application is the detection of fire, and the second one, which is not so interesting, is missile tracking. Good. So why is this interesting is because you have a signal to noise ratio which is high, the noise being the background and the noise being very low, so the signal ratio is very high, and therefore this technique is quite sensitive. Okay. And for that technique to work, you need this type of spectral response where you are sensitive to UVC radiation only below 280 nanometers. So you need to be solar black. You need to be not sensitive to this solar radiation. That's the point of this solar black detector. Good. There are many other applications of UV, so I will skip that and come back to fabrication of photodetectors. So for the photodetector, what you need is single crystal. That's the things that make good crystal, a good photodetector. You need single crystal metal. And the conventional way to fabricate a single crystal is to make them in the form of a thin film. And for that, you rely on the epitaxial force technique. And for that, you need a lattice match substrate. So these are very powerful, very nanowires, because nanowires are in the form of a single crystal. So they should also be good photodetector, but you don't have a way to assemble them. So you can get nanowires, but it's difficult to assemble them to make two electrodes, for example. So this is what we've been trying to do. So that shows the standard technique, the top-down technique that is used in laboratory to make the detectors. So you start with messy nanowires, disperse them, put them on a surface, then look for the nanowires, do mark, and then use this process here to fabricate two electrodes. And then you have your detector. This is a single nanowire detector. So it's very interesting because it allows you to get the fundamental properties of the nanowires, but it's not very practical as a means to make a sensor. It's not very practical. A lot of steps. Good. Yeah. These are the properties that we get with these single nanowire devices. So it's a bit of a sluggish response to the UV here and here. And sometimes you start at this level, this is the dark current. Response to UV, you don't come back at the center. So there are a lot of small parts of this type of design. Okay, so what we propose is to fabricate, to grow thick layers, two thick layers of nanowires that are full of defect actually. So they have a very low resistance, and to reach them with nanowires. That's the simple technique that we have. So the part that is sensitive to UV is the nanowire here in the middle. And this thick layer are used to contact, to make the contact, to get the signal. Okay. So what are the advantages of this simple technique? It's very efficient, cost effective. We do not resort to lithography step. Okay. There's no lithography step. So there is no contamination of the nanowire. Lithography implies that you use basis, so then you contaminate the substrate. And the bridge here are not in contact with the substrate, so the nanowire, the properties are not affected by the substrate. Okay, so this is just to show you that we actually make the map, the sense or the sensor by ourselves. So it's very easy, and then we can contact them like this. And this shows the cone, so you have the plus and the minus here, and the cone electrode here. So in between, the part that is dark here is just the bridge part that you don't see, because the nanowire density is very low. Okay, good. How do you make them? It's very easy. We start with a physical mask. Physical mask is something that you can fabricate with chemical etching. It's very, very cheap, very convenient, and because it's made with a chemical etching, it means that the gap that you have here are larger than 100 micrometers. So we use that, sputter gold through that mask to get the shape of the mask. And the gold here that is sputtered, a very small amount, is used as a catalyst for the growth of the nanowire. So the gold defines where the growth takes place. It's selective growth. Defined by the gold. Okay. And then we grow these nanowires. So we have a large growth on the gold, and we just have to select the growth parameters to obtain very long nanowires, because the gap is 100 micrometers here, and randomly some of the nanowires will reach from this electrode to the next. That's as simple as that. Okay. So the furnace that we use is very standard one. We just feed you thick oxide powder and form this vapor that is made to react on this substrate with oxygen fluid. Good. So this are the results. That's for the count structure here. So in dark here, what you see is a gap. If you zoom in here, you see some bridge like that. And this is a finger structure. Again, in the gap here, you have nanowires connecting the two electrodes here. So cones are very nice to make large surface detectors. These are for array detectors. Good. So this is the main result that shows you that actually it works quite well. This is a cone detector. So BC between the point BC, what you have is a thick layer here. So you measure the characteristics of the thick layer in red here. It doesn't like bounce of UV. So you start with a very large dark current, and you have a low response. So this is not very exciting. This is just a response of a thick layer of zinc oxide throughout the planet. Now, if you measure between the point A and B, you have to cross through the bridge, and then you start with a very low dark current, and you get a much more exciting response with 4 orders of difference. This is a large scale. Good. So this is a large increase, and you have a kind of sluggish decrease in this region that I will try to explain. Good. So the slow response is a bit difficult. This is due to kinetics. You get a rise here, a slow rise here, and a slow decrease here, and they are both explained by kinetics in the sense that oxygen molecules trap electrons and deplete the zinc oxide nanowires from electrons. And that's what you have in the zinc oxide. And when you eliminate with UV, what happens is that the oxygen is dissolved, and this is the slow reaction because this is kinetics. And then put back in dark, then oxygen is reabsorbed. And that's what you see here for the reabsorption and here for the desorption. Good. Okay, so we can make a different kind of bridge. We can form a junction in the middle of the gap here that gives you like a double Schottky barrier like IV curve like this, and a very fast response of the current, or direct bridge that is almost ohmic and kind of interesting response, or very thick layers that are not very interesting. So this is the way we control the response between different kind of bridges. Okay, so the final story of that with the bridge structure is that we have done that with zinc oxide, and now we do this. We apply the same process with the gallium oxide, which is a very large bond-gap material that is selective to UV-DPUV. You can see the result here. So the material, gallium oxide here, is not sensitive to radiation above 280 nanometers. So this makes you, this gives you a solar blind property. Good. And this is shows the response of the device, which is quite good with a very low dark current and a very large increase in the current. So it works quite well. The response is very fast. The main difference between the two materials, as explained here, so zinc oxide has a lot of defects, and therefore you have kinetics and a little slow time problem with the time response. For gallium oxide, you don't have this problem, so the surface reaction is not there, and it gives you very fast response directly. Okay, good. So that's for the story about the horizontal integration of nanowires. So the next point is to use the vertical nanowires with a core shell structure that I will explain right now. So we do water splitting with this vertically aligned nanowires. For water splitting, what we have is a photoanode and a photocathode. But what we do, what I do in this presentation, what I show in this presentation is a photoanode story. Okay? So the light is coming from the left side here, you make the photoanode, and you oxidize water and form dilute oxygen. Here on this side, on the cathode, you will dilute hydrogen. You can do the reverse as well. Use a photocathode and an anode, or both the photocathode and the photoanode. There are plenty of configuration. So the main point here is the design of the photoanode. So what is convenient to use nanoparticles. Nanoparticles provide you with a very large surface for chemical reaction. So this is a very nice point of the nanoparticles. However, the charge transport is limited by the boundary here, so charge transport is not very good. And on the opposite, you could use a film electrode, so a bond material, single crystalline type material. In that case, the charge transport is very good, but you don't have surface for the chemical reaction. So the idea is to combine both a nanoparticle and film electrode, and this is the type of design that you have, where you have the nanowires on the top of a single crystal material here. So this part here is used to transport the electron, to the cathode, and the nanowires are used for the chemical reaction. The point of this design is that this things here, the nanowire film, the nanowire on a film structure, at best should be in the form of a single crystal, which is very difficult to fabricate. Okay, so we are trying to fabricate that with zinc oxide, and I showed the result here. The process is very easy. It's a chemical rate of deposition that is controlled by again gold catalyst on a sapphire substrate. So show here is the filter field of the result of the gold. So you can see many nanowires vertically aligned with quite high density, and this is the top view of the same sample, where you see that the crystal here, the crystal, the top view, the top of the nanowires has a beautiful hexagonal shape, which is the shape of the crystal actually, and all facets are aligned, perfectly aligned. So this is a good indication of epitaxial gold actually. So they are all aligned. Okay, so it's likely it's epitaxial gold. Good. And the proof of that is by doing electron diffraction analysis. So we have the cross section here, the substrate, the thick layer, nanowires, and when you do electron diffraction of the layer and of the nanowires, you get the same diffraction pattern. So it means that both are aligned, and therefore they form a single crystal. On a larger scale, we do also the X-ray diffraction and obtain only two peaks, so 002. That means that the plane is aligned. So this plane here, because plane is this one, and the working curve is extremely, the width of the working curve is very narrow, so it means it's a good indication of a good crystal. And finally, you have the pole figure here, which has 6 dots here, 1, 2, 3, 4, 5, 6, which is the typical pole figure of an hexagonal crystal. Hexagonal means you have a 6-fold rotation symmetry, 6-fold symmetry, and therefore 6 dots here. So that is a proof that the material is in the form of a single crystal over quite large area. Okay, so the next point was to check the optoelectronic quality of that material. We did that by low temperature photoluminescence and observe the free exciton emission here in this region. So this indicates a good material as well. So now, before to look at the result, just very briefly explain the reason why we have a good single crystal. Actually, we grow the temperature at high temperature, and we grow the material at very high temperature, and for that reason, we form an intermediate layer between the substrate and the zinc oxide here, and that intermediate layer is a spinel phase that enable reduction of stress. So that's the reason we can get a very nice single crystal. And at the end, what we have is that the sapphire spinel interlayer and the zinc oxide nanowire film structure in a single crystal form. So this is the schematic of the material that we have fabricated. We can control the thickness of the, here you can see better, the thickness of the layer, the underlayer layer of zinc oxide here, and the height of the nanowire by changing the amount of gold that we use to control the gold. Okay, so the next step now is we use a zinc oxide nanowire on the film structure as a template to do this water splitting experiment. Zinc oxide is not very stable in water, so we have to protect it, so we have to cover it with a layer that we make it stable, and for that we use the zinc gallic, gallic phase, so zinc gallium oxide to fabricate a core shell structure. This is just CVD process and grow this shell on the top of the zinc oxide to protect the zinc oxide, because zinc oxide will be dissolved in water if it's not protected. Good. Okay. So this is the zinc gallic phase here absorption and the zinc oxide long edge absorption. So both are there, that's for sure. and I show you the result of water splitting here. So this is the on-off current. That's 0 means the dark current. So you see that the dark current is 0 when we increase the voltage. So this is a very important information. We are not, by increasing the voltage here, we are not changing the dark current. It means that we really are doing water splitting here and not split the water by just applying the voltage. Okay? So this value here is the photocurrent on the illumination, and dark current very low here. So what is important is the stability of the process here in time. You see that it's pretty stable, so the current is stable in time, and you compare that with results published on zinc oxide nanowires, where you see a quite strong decrease in the current as a function of time, because the zinc oxide is being damaged by the photocatalytic process here. So our process allows us, so this shell allows us to protect the nanowires. Okay. The final thing that we did was to use a nitridation process to increase the absorption of light. So at the end, what we have is the template made of zinc oxide nanowire on a film structure, and the shell now is more like this material. It's a zinc galide oxynitride material that is quite a famous material. Water splitting, and that is stable and allow us to absorb a bit more in the visible region. So with that material, we have again stable water splitting current here. So the photocurrent is stable in time for 30 minutes. We can the experiment is also reproducible, so we can reproduce our result over a month. And what is nice in our case is that the onset of the voltage for water splitting is quite low compared to other materials. For example, hematite, which has a very quite large value for the onset of the water splitting. So the problem is still the efficiency. The current is a bit too low compared to other materials, so we still have to work to increase the efficiency of that material. 1.5 milliampere per centimeter square is not such a high current. We should get something like 3 or 5 to get quite efficient material. Okay, so in conclusion, what we have done here, we have found a technique to fabricate single crystal domain and higher optoelectronic quality of zinc oxide nanowire on film structure, and we can use this as a template to fabricate core shell nanowires of zinc galide oxynitride phase, and this the core shell material is stable under water splitting condition and deliver a current of a photocurrent of 1.5 milliampere per centimeter square at 0.8 volt. Actually, so this is the final result that we have with this material. Okay, and that's the end of the talk. Thank you for your attention. Okay, so if you have okay, so somebody.
I'm trying to understand that all the electrochemical process, is that treated as a battery or treated for the water splitting?
This is water splitting.
You draw a circuit, is that also a kind of an electric circuit generated from electricity from that system or not?
Well, it's not the story is not here to generate electricity. You don't use that to light up. You use it to generate hydrogen.
Okay.
And the hydrogen is stored. And then this is the transformation or conversion of solar light into chemical energy, which is hydrogen.
Okay. All right.
Okay. That's the purpose of this thing. Good. Any other questions? No. Okay. So then we ask the second speaker.